Hi, my name is Emma Brunskill. I'm an assistant professor here in the computer science department, and I'm really delighted to be here or virtually here to talk to you about some of the work that we're doing in my group. I just want to start off and say that many of you might be familiar with some of the incredible successes we've been seeing in artificial intelligence over the last 5 years. Things like automated AI agents that can play video games as well as the best humans, robots that are having some incredible capabilities in terms of manipulating objects, and the first success of the AI system that can beat the world best players in Go. And in all of these cases, these systems have reinforcement learning, which is the area that I work in, underlying them. And I'll talk more about what that is in a second. But I just want to start off and highlight that you may think because of all these incredible successes that perhaps artificial intelligence is near done, or that this field of reinforcement learning has already peaked and the main successes have already come. I just want to highlight that I think that that's not the case. If you look at a simple example that us in academia deal with all the time, there's this instance of office hours where, let's say for the very first time when I'm teaching a class for a new assignment, then I have to figure out for the line of students that are waiting to come talk to me, how best to help them work through a new assignment. And this is really a very complicated problem. It involves partially observable decision making. I don't know exactly what the student knows or doesn't know. I need to figure out strategies to quickly help them reach a good level of understanding. And I want to do so in a way that is effective and efficient, not just for this student, but for me to identify strategies that are going to help all students. Now, this sort of very complicated decision-making process is something that all teaching assistants in America, thousands of people, are going through all the time and doing so relatively very effectively. And yet it's something that we don't have any AI agents that are capable of doing yet. And more broadly, this area of sort of sequential decision making under uncertainty has a very rich history and has been around at least since the 1940s. And while the probability and statistical problems involved have already been identified as formidable, from the very beginning, people recognized that if we could solve these sorts of problems, they would have huge implications for mathematical statistics and to science. And so really, I'm very interested in this question for two reasons. One is that quickly learning to make good, robust decisions is a key part of intelligence, and so it must be a central part of any agenda to achieve general artificial intelligence. But secondly, I think that if we want to use artificial intelligence to tackle and realize its potential to help us in many domains of societal importance, then we need to think about how to make decisions under uncertainty. And the majority of my work can really be framed within this sort of deceptively simple question of how can we do machine learning from limited samples in order to robustly make good decisions. I just want to highlight that in my lab, we think about this from several different angles. I think about this from particular application domains, particularly things in the context of education, which I think has enormous potential to improve people's lives, as well as healthcare. And these types of applications motivate and drive impact. And the second is that we do a lot of work on algorithms, which help formalize our understanding and provide tools. And finally, we also do a lot of work on theory because I believe that allows us to ground and solidify our understanding. Now, I want to sort of just briefly today talk you through some of the different areas that we're thinking about right now, as well as do a tiny bit deeper dive in one of them. So one example you might have heard about last fall is that OpenAI, a relatively local company up in San Francisco, devised a robot that could successfully manipulate a Rubik's Cube and solve it much of the time. Now, if we look at what was needed to achieve the success, the paper notes that the amount of experience needed was about 13,000 years of compute time. Now, if we do sort of a back of the envelope calculation, what we would estimate here is that perhaps the computer needed around 197 million attempts in order to successfully learn this consistently. Now, that seems like a lot. That's a lot more than we would expect any humans to need, but perhaps that's okay. We live in the age of big data. Maybe that's the amount of data that we could hope to have for the new applications we consider. Well, to think about this, I like to think about fitness because I think that fitness is an area where we could imagine there's a lot of wearable devices now, and this might be somewhere where we could imagine using decision making under uncertainty to help people achieve their health and wellness goals. Now, the Fitbit is one of the most popular devices out there. And it's been used by millions of people. But if we look at how long it's been around and how many devices have been sold, to get a sense of how much data we might hope to be able to get for this, it's only had about 90 million ever sold since the company started around 2007. And what this argues to me is that while we do live in the age of big data, the amount of data that we're getting about sort of sequences of decisions and their outcomes, it's still limited in the context of thinking about applications that might help people. And that argues to me that we really need machine learning tools that can learn efficiently, that can learn from limited amounts of data, limited amounts of samples. And so a large amount of our work thinks about this technical question of how to be statistically efficient in these cases. What can we squeeze out of that data? Another part of our work comes from another part of this question of how to sequentially make good decisions. And this is really inspired by a lot of work on intelligent tutoring systems and using AI to enhance education. And in this setting, one of the papers that I think is super interesting in this space is about 20 years ago, there was a reinforcement learning system that was designed to try to identify problems to students in a way that it would help students to do problems quickly. Now, the authors weren't trying to say this is the final goal of education, but this was sort of one of the first systems to try to start thinking about the educational problem. Of course, there's other work, but from a reinforcement learning perspective. But if we contrast this to what are the goals of education, I've put up here just one of the pages that describes the goals of the education in the Palo Alto School District, which is where I live. And you can see here that even on this single page, there's an enormous number of types of objectives and goals, and they include things that seem perhaps quite reasonable to optimize from an intelligent tutoring system perspective, things like performing at or above grade level. But they also include much more complicated things like helping students discover and pursue passions, and for the overall system to promote equity. And so I think when we think about sequential decision making under uncertainty to achieve some utility or objective, it's really important to think about what does it mean for a system to be good, and where are we getting these sort of objectives from, and how can we partner with domain experts for the type of applications we care about so that we can be sure that we're really trying to best fulfill the desired objectives of the different sort of stakeholders in these type of applications. Now, so I also just today, though, want to talk particularly about a third thing that we focus on a lot in my group, which is thinking about learning from limited samples to robustly make good decisions, and really thinking about what we can do from past data. So this is sort of the challenge of thinking about what if reasoning. So imagine that we have a series of electronic medical record systems, a series of electronic medical records about patients and interventions and those patients' outcomes, which could be things like mortality rate, it could be sort of aspects of blood pressure control, it could be all sorts of different types of objectives. Now imagine in this case we have 3 different individuals and they've had different sequences of outcomes, a different sequence of treatments and outcomes, and then we have a new patient coming in. And what we want to be able to do is to figure out a good strategy for that new individual. Now this is a really challenging problem, and it's a challenging problem for several different reasons. One is the sort of censored or counterfactual aspect of this data. And what I mean by this is that we can never go back and sort of rewind the clock and treat the same patient in a different way. So in this case, I couldn't see what would happen to the woman if I had treated her in a different way. Perhaps if we had done a medical exam first and then done a medication intervention instead of starting perhaps with some pre-prescribed pills and then a follow-up checkup. So I can't see what would be the differences in outcomes if I could rewind the clock and take a different sequence of actions or interventions to help the patient. And this is a really big challenge because when we're trying to think about how to best help a new individual, we'd really like to be able to know what would happen under different types of sequences of interventions. The second challenge is sort of what I would call the need for generalization, which is here I'm just showing you two different treatment decisions. So perhaps do we start with a checkup and then have some medication? Do we start with a checkup and then have an injection? And here there's sort of just, two different time steps on where we're making decisions and perhaps a small number of interventions. But in general, you can see that this could grow combinatorially, like the space of different sequences of health interventions we could do is going to grow exponentially with the number of decisions we make. And so it's simply not going to be feasible for us to do a randomized controlled trial to consider all of these different types of sequences. And therefore, that means we're going to need some type of way to hopefully generalize from past experience to try to interpolate or extrapolate to think about whether we can use this data to figure out how to make better decisions in the future, if that's possible. Now, the framework that we use to think about this, of how can we take this old data about decisions made and their outcomes and figure out new future strategies for making decisions based on the state of the patient or the state of a customer or the state of the student. We typically, in my field, think about this through the lens of Markov decision processes. So we think of there being sort of some state of the system, which would, in this case, would be like the state of a patient or state of a student or state of a customer. And then our automated system has a policy, which we often denote by pi, which is a mapping from states to actions. And so this action could be things like prescribing a medication. And then we see some sort of measure of the success of that. So some sort of reward that's based on the state of the patient and the action we took. Now, sometimes some of those things might be delayed. We might not get to observe for a while what the outcomes of those decisions made are, and it might be that we're looking at mortality rate, which might be after 5 years, what are the outcomes for the patient? Now, the way that we measure and compare different strategies or policies is by looking at the expected discounted sum of rewards. So if we add up all of those sort of reward signals we care about, which again could just be mortality, then how well is our policy doing? And then we think of better policies as ones that are better maximizing these reward signals. And one of the big challenges here is that generally we assume we don't have a good model in advance of how the system works. What happens if we take a certain action in a state? So if I prescribe a particular medication, diabetes medication to an individual, does it help them manage their blood sugar in a way that's very effective? So often we do not have perfect models of the physiology of individuals. And so in many cases, these are only observed through data, through samples. And the challenge in counterfactual or batch reinforcement learning is the idea that we have access to a data set of previous decisions made and outcomes, so maybe a series of electronic medical record systems. And what we want to do is to try to mine for natural variability in that data to try to see if we can make better decisions in the future. Now, this is sort of a general question of causal inference and machine learning, and this is becoming a very exciting topic right now because a lot of people are thinking about how can we learn models that are not just predictive but will allow us to make different decisions. However, most of the prior work, which also spans other fields like econometrics or biostatistics, the majority of the prior work focuses on making a single binary decision. So things like treatment effect estimation, how much better is a treatment than a control. But when we think about doing this for Markov decision processes, in many cases we're making not just one decision but a sequence of decisions. So in many cases we're thinking about a sequence of interventions that are made to try to maximize for patient wellness. So maybe we have to use ventilation or sedation or provide a vasopressor. And so we get this series of decisions that are being made over time. And one of the key questions here is that if we want to think about doing things in a different way than we've done before, then only probably part of our data will match the type of decisions that we're interested in evaluating. So maybe we want to consider policies where we both apply mechanical ventilation in a certain state, and then if the patient experiences discomfort, then we use sedation. And it may be that in many cases, those type of decisions were not made for patients. And so our sort of effective sample size gets smaller over time. So we've been doing a lot of work in this space, and there's sort of a number of different central questions for batch reinforcement learning. And one of them involves sort of off-policy evaluation, estimating the performance of a new decision policy. And in this sort of case, we're interested in, let's imagine we have a particular strategy that we want to evaluate, and we want to think about how good it is and maybe be able to get some sort of confidence over its expected performance. Another challenge we often want to think about is off-policy optimization, which is we actually want to go into that prior data and try to figure out what works best so we know that we can use that in the future. So let me just give you one really brief example about the second thing. And I'm not going to have a chance to go through all of these today, though I'm happy to talk about it in the panel. So let's think about something like diabetes insulin management, and that we have some historical data, and we have a decision policy which is saying from some physiological state of the individual, what insulin dosage should we give? And when we're doing this, we may want to sort of optimize for long-term outcomes, some sort of measure of blood sugar control of the individual, but we also may have side effects that we want to minimize, or we may want to minimize the amount of time the blood sugar is very high for the patient or low, and we may want to have hard constraints on that. And in general, this goes back to sort of this challenge I was mentioning too about what does it mean to be good? And so in many cases, we're going to want to not just sort of optimize an expectation for an outcome, optimize on average, but we may have hard constraints either due to safety or side effects or fairness guarantees, with respect to men and women or different racial groups that we need our decision policies to satisfy. And so together with my former postdoc, Phil Thomas, and a number of other wonderful colleagues, a few months ago, back in November, we published a science paper providing some different ways to think about how do we optimize for one objective while ensuring that the solutions we get satisfy some desired constraints. In particular to avoid undesirable behavior. And we thought about this for this sort of fairness aspect as well as safety. So in this case, I'll just say very briefly to give you a high-level idea, we think about this for the algorithm we use for the diabetes case of thinking of there being sort of a number of different decision policies that we might want to deploy in the future. And we also have some constraints here, things like ensuring that there's no more hypoglycemia than some desired threshold. And what our algorithm allows us to do is to find solutions that with high probability, with high confidence, are going to satisfy those desired constraints in the future. And one of the interesting things here too is it'll tell us if we don't have enough data in order to satisfy those constraints. And I think that sort of transparency can be very helpful now because I think being able to know when our algorithms are able to meet the desired criteria that we need to be competent in deploying them can help build trust by providing more transparency. So in this case, we applied our approach to diabetes insulin management. The question was, how do we do blood glucose control? The decisions the algorithm is making is what insulin dosage to provide. And we were searching over different decision policies. And our constraint was to avoid hypoglycemia. And what we used in this case, this was not a patient study, but we used a very accurate simulator, which was actually approved by the FDA to replace early stage animal trials. So it's really trying to do a good job at mimicking some of the basic physiology. And what we can see in this case is that on the x-axis here is the amount of days. So we're thinking about gathering data from an individual over time using some default policies that are considered to be acceptable. And what we're trying to do is to find better policies that are better able to satisfy desired constraints in terms of these side effects on hypoglycemia and or in terms of their expected management of blood glucose. What you can see here is if we use sort of some standard alternative approaches that don't try to satisfy these constraints, they're always able to output a new solution, but they may violate our desired safety constraints instead of hypoglycemia, around hypoglycemia. Whereas what you can see for ours is within about 4 to 5 months, so around 150 days, our algorithm can reliably provide a solution that is able to satisfy these constraints. And we can see that here too, is that we can sort of quickly be confident that we have identified a more safe policy. I'll just say here briefly, in that first work that we looked at, we thought about first sort of a finite set of decision policies. One of the big benefits right now is they came out kind of infinite numbers of strategies, and we've started to extend this work in a recent NeurIPS machine learning paper to think about this, where we thought about this for one-time step decision making and applied it to fairness constraints, like across different genders, and it could also be applied to racial groups. So just to summarize here, I want to highlight that there's sort of a lot of really important questions about how do we better leverage prior data, and can we leverage natural variation or explicit variation in decisions in order to improve future decision making. And it also is really extending our machine learning techniques as we try to be able to tackle this. And to conclude, my goal in my research is to ultimately really focus on this human side of applications. And the final goal is to really develop continually improving human reinforcement learning systems that are worthy of the people they serve. Thank you very much.